Hello and welcome to NPTEL MOOC on electromagnetic waves in guided and wireless media. So this is module 17 of the course, and we have already seen uniform plane waves, the wave equation, and we have seen different type of polarization. In the last module I gave you an exercise. Let me first solve that exercise to show you that we don't only have linear polarization, but we have polarizations of different nature as well. Okay. So we took the electric field to be of the form x hat a at z equal to 0 plane. Of course, we took this as x hat a plus y hat a e power minus j pi by 2. Now I will first convert this phasor at z equal to 0 plane into the real time dependent expression. So I will now have x hat a cos omega t plus y hat a cos omega t minus pi by 2. Okay. Now cos omega t minus pi by 2 would actually be equal to sin pi by 2, right. So I will have, instead of writing this as cos omega t minus pi by 2, I can write this as sin pi by 2, right. So when I write that, what I will have is I wrote cos again, it's actually sin omega t, right. So cos omega t minus pi by 2 is sin omega t. So now this is what we have in terms of the time dependent electric field. Okay. As before, we will draw the axis, mark x and y. Okay. And now look at what happens at omega t equal to 0. So at omega t equal to 0, cos 0 is 1, sin 0 is 0. So the electric field has to lie entirely along the x axis with an amplitude of a, right. So this is the situation at omega t equal to 0. Now what would be the situation at omega t equal to pi by 4? At omega t equal to pi by 4, both cosine and sine have equal amplitudes, and because you have x hat a plus y hat a divided by root 2 on both sides, the angle with which the resultant vector will be at 45 degrees. Okay, so that would be 45 degree angle. However, the amplitude of this one would be at a by root 2 plus a by root 2. Okay, that would be square root 2 times a, and you can plot that. So you have a here, and then you have a here, and then a by root 2. So what you will actually be able to find out is to find the magnitude of this one, and then write the vector at omega t equal to pi by 4. Okay. Now what is the situation at omega t equal to pi by 2, in which case cos pi by 2 will be 0. So the x component will contribute to 0 length vector, whereas the y component will contribute to the full a magnitude length vector. Okay. So you actually have a here at omega t equal to pi by 2. Now you can see a pattern emerging, right. So as I start increasing omega t further, I will note that the field vectors seem to be going along a particular circle, and they would be moving in this particular direction, which is basically counterclockwise. Okay. So because you move in the counterclockwise direction, so you can actually start with x and y, and then when you move in the counterclockwise direction, your thumb will be pointing along the z axis, right. So you start off with x axis, which is your where at omega t equal to 0 the electric field vector was, and then you move your fingers along or curl it along the direction of the increase changing electric field vector, and you will see that your thumb is pointing along the z axis, and you have actually used your right hand in order to get to the plus z axis, and this is therefore called as right circularly polarized wave. Okay. Or sometimes called as right handed polarization, right hand circularly polarized. Why it is called circularly polarized? Because these electric field vectors are moving along a particular circle of radius a here, correct. So this is right hand circularly polarized wave, or sometimes simply called as RHCP vector. Okay. You can show, I will leave this as an exercise, that if you change the phase from minus pi by 2 to plus pi by 2, you will end up with a left hand circularly polarized vector, which would actually move in this direction. Okay. So it would move in the direction that is opposite to that of the right hand circularly polarized wave. So you do have different types of polarization. Linear polarization is one where the phase difference phi x minus phi y will be equal to 0, and you have, let us say, the circularly polarized version. You have two types of circularly polarized cases. One, you have the left hand circularly polarized wave, and then you have right hand circularly polarized wave, depending on whether the phase phi x minus phi y is pi by 2 or minus pi by 2, and then in the most general case is when you have what is called as elliptical polarization. In the elliptical polarization, you can still have it along, I mean the movement of the electric field vectors can be either left or to the right, okay. However, they would not move along a circle, but they would actually move along the ellipse that you can see here, okay. So, they would actually be moving along the ellipse. Both kinds of ellipses are possible, left handed ellipse and the right handed ellipse. So, these are the different types of polarization of a uniform plane wave. Now, let us go back to the type of media that we were considering. We considered a linear medium, which is fine, we will still consider the same medium. We consider isotropic medium, meaning that your direction of the propagation would not matter, the properties of the matter would remain the same whether your wave was propagating along plus z direction, oriented along x or oriented along y, okay. Then we have a homogeneous medium, meaning that the material properties, say the permittivity and permeability, would remain constant or it would remain the same at different points in the space. And finally, we had considered the lossless materials, okay. In the lossless material scenario, what we had was the material made out of pure dielectric, meaning that epsilon r was present and any conductivity of the medium that could normally be present in a typical medium was actually taken to be equal to 0. So, the material was pure insulator or pure dielectric, okay. Of course, we have non-magnetic medium which we will continue to use. Now, what I want to do is to relax this assumption of losslessness. I mean, we want to consider after all propagation of waves in real media, and most real media will actually be lossy, right. So, if you take a glass slab for example and then send light in, right, and then you measure the power of the light that is coming out and compare it to the power of the light that was put into the glass slab, you will see that there is some difference. That difference is actually being absorbed or is the result of absorption of the electromagnetic wave, some part of the electromagnetic wave by the material itself, okay. What it does is to slightly change the temperature of the material, but we will not worry about that one. For us, whatever that has gone in is not the same as that is coming out of the medium, then it means that we are considering a lossy medium. Of course, we could also have the output of a particular medium having a power which is greater than the input power. In that case, we would be considering what is called as active medium or gain medium, okay. We will not consider the gain medium in this course, we will stick with lossy medium, okay. Now, I have already given you a hint as to how to approach modeling of a lossy medium, okay. Lossy medium can be modeled by letting sigma be non-zero and having some finite value of that. Now, the notable change that would happen in Maxwell's equation for such a lossy medium is this curl expression or the Maxwell-Faraday expression, wherein the previously neglected term which is J is now brought back into it. So, which is given by sigma E plus, assuming still that we are working with phasors, I can write down the phasor expression as j omega epsilon times E, okay. This comes from another observation done in perhaps a different course, that conduction current density is actually proportional to the electric field, and this proportionality constant is called as the conductivity of the medium, okay. And this conductivity carries units of Siemens per meter. The old notation was Mohs per meter. Now, this is the preferred SI notation of Siemens per meter, okay. And of course, it makes sense because J is current density, which would be measured in ampere per meter square, and this fellow is Siemens per meter, and there is a voltage V per meter. So, V into S is like voltage times conductivity, which is basically current, ampere. So, ampere per meter square is what you are going to get, okay. So, this is the only change that would happen in your Maxwell's equations. The other equations are as they are, okay. So, you can even simplify this expression by writing this as sigma plus j omega epsilon times E, and I can write this as j omega epsilon C times E, okay, where you can see that epsilon C is a parameter that I have simply introduced, and this parameter should actually be equal to some sort of a that would actually be complex, and that should be related to sigma and epsilon. How should it be written? So, we know that j omega epsilon C should be equal to sigma plus j omega epsilon if these two equations have to remain the same, and then I know that epsilon C is a complex permittivity that I have introduced, which I can write it as epsilon prime minus j epsilon double prime. Okay, so I now have j omega epsilon prime minus j epsilon double prime should be equal to sigma plus j omega epsilon, okay, where epsilon is your original epsilon that we had considered, not the complex permittivity that we have considered. So I can write this as j omega epsilon plus j omega, sorry, j is not there because that is gone now. So omega epsilon double prime, this should be equal to sigma plus j omega epsilon. So the complex part can be equated to this one, saying that epsilon which we had taken is actually the real part of the complex permittivity epsilon prime, and then whatever that is left out, omega epsilon prime is equal to sigma, alternatively epsilon double prime is equal to sigma by omega. Okay. So I can write the equation without changing anything by simply introducing this complex permittivity epsilon c and working with the entire thing, identifying that the original permittivity of a lossless media can be taken as the real part of the complex permittivity. Okay, so this is something that I can do. Okay, in fact, you would see epsilon prime and epsilon prime being used in many electromagnetic materials that we considered. So what we have seen is this epsilon double prime can be written as sigma by omega, and this can be included to talk about the lossy medium. Okay, let us now see what happens to the wave equation when we include this lossy materials or lossy medium. So I have del cross E equals j minus j omega mu naught h as before. So there is no change in this one, and now I will take the curl of this electric field again. So I will get curl of electric field, sorry, I should take the curl here. So this would be curl of the electric field, that should be minus j omega mu naught, and then I will end up with del cross h, which as I have seen can be written as sigma plus j omega epsilon times E, or equivalently I can write this as j omega epsilon c times E. Okay, I will go with the former because I want to bring in the transmission line analogy as well. So I am going to use the full expression for complex permittivity. So I will write this as sigma plus j omega epsilon only, and in this case epsilon will be a real quantity. Okay, sigma will of course also be real. Okay, the left hand side we have already seen can be reduced down to minus del square E. Okay, the presence of conduction current densities does not alter this equation del dot D equal to 0. Okay, this equation will still remain the same, and consequently del dot E will also be equal to 0, and in this expression of the vector Laplacian you will see that when you expand this out, that del of del dot E term will go to 0. So I am having on the left hand side a minus del square E, which of course would be on to the right hand side given by minus j omega mu naught sigma plus j omega epsilon times E. Okay. Minus sign can be cancelled off, and also considering the fact that we are not looking at waves in arbitrary direction, we are looking at waves which are propagating along the plus z direction, and x polarized waves is what we have been considered, x polarized linear waves that we have considered. I can replace this del square simply by del square by del z square, right, which is what I am actually interested in. And when I do that, I will have del square E x by del z square to be equal to j omega mu naught times sigma plus j omega epsilon times E x. Okay, so this would be the expression that I would have. Of course, instead of del square by del z square, because we are dealing with a phasor, I can simply write this as d square E x by dz square. Okay, I can now write this entire thing as say gamma square E x, and my solutions with respect to z, the phasor solutions with respect to z will be some amplitude which we will call as some Ex0, and because we are considering plus z direction wave, so we can write this as e power minus gamma z. Okay, where gamma square is equal to j omega mu naught into sigma plus j omega epsilon. Okay, or gamma itself is equal to square root of j omega mu naught sigma plus j omega epsilon, which can be further written as alpha plus j beta, and alpha is the real part of gamma, which is called as attenuation constant or attenuation coefficient, and beta is the imaginary part of gamma, which is called as the propagation constant or the propagation coefficient, okay, and this is given by square root of j omega mu naught into sigma plus j omega epsilon, that gamma. Now, if you recall the transmission line where we have taken, say let us assume that we will take r equal to 0, we will take g not equal to 0, we will take L not equal to 0 and not equal to 0, C also not equal to 0, then this gamma expression in the transmission line case would actually be given by j omega L times g plus j omega c. Is that correct? Yes, because I have taken only r equal to 0. These I am neglecting the series resistance of the wires. I am assuming that the wires actually have some amount of, or the material that I have considered is lossy material, which is modeled by having this conductance G there, right. So, this was what your gamma in the transmission line expression would look like, and now you can see that it would essentially be similar to the expression that we have written in a lossy medium. Here also the transmission line was lossy because of the presence of this G, and clearly because G is kind of similar to sigma, this corresponding medium is now lossy as a result of this. So, the expressions that we have written for gamma is essentially similar to the expression that we have written or used in the transmission line case as well. Now, you may also find out that the impedance that we are going to write, earlier the characteristic impedance of a transmission line when it was lossy was given as r plus j omega L divided by g plus j omega c under root, right. So, by taking this analogy between the transmission line and the lossy medium that we are considering, the characteristic impedance or the wave impedance or the intrinsic impedance of the medium when the medium is lossy would be correspondingly given by j omega mu naught divided by sigma plus j omega epsilon. This expression equals eta naught, that is eta will be equal to eta naught when sigma is equal to 0 and epsilon is actually equal to epsilon naught, correct. So, this expression that we have written, the medium impedance or the wave impedance or the intrinsic impedance, this would be equal to the, it would be similar to the expression for a lossless or lossy transmission line, okay. So, this is the propagation of wave in a general lossy media. There are some situations where this sigma is very small compared to omega epsilon. In this case the medium is mostly a dielectric medium, okay. However, at different frequencies it may not remain a dielectric material. When sigma is much greater than omega epsilon, then you have a pure conductive medium which is very lossy, okay. That is the reason why most metals actually are very lossy at very high frequencies. They are basically, their sigma value becomes very high, omega epsilon. Of course, you can bring them to be kind of a dielectric, but you have to actually increase the value of omega to very large extent there, okay. So, it is also interesting to look at what would be the expression for gamma when it is pure dielectric. When it is dielectric, we know that gamma is given by pure j omega square root of mu naught epsilon, okay. Epsilon equal to epsilon naught will give you the propagation constant in free space, epsilon naught equal to epsilon naught, epsilon r will give you propagation in a dielectric medium where this condition holds, that is sigma is so small that I can neglect that one, okay. And the corresponding impedance is also going to be quite real, it would be square root of mu naught by epsilon, okay. This is for the dielectric scenario. On the other hand, for the conductive scenario, gamma will be equal to square root of j omega mu naught, okay, sigma, because j omega epsilon is very small compared to this one. So, gamma will be equal to square root of j omega mu naught sigma, which of course will be equal to alpha plus j beta, correct. Any complex number is equal to real and imaginary part. So, what is alpha here? In fact, the magnitude of alpha and beta both are equal and they are given by omega mu naught sigma by 2 under root, okay. Why is this? Because I can write this square root of j omega mu naught sigma as square root of e power j pi by 2 omega mu naught sigma. This can be written as square root of e power j pi by 2 times square root of omega mu naught sigma, and the square root of e power j pi by 2 is basically e power j pi by 4, which is actually 1 plus j by root 2. Okay. So, now you can see that alpha and beta both should be equal to square root of omega mu naught sigma by 2. So, this actually means that the medium is lossy, but also has a propagation constant, lossy but has a propagation constant beta whose magnitude is actually equal to alpha. Okay. So, this is a very interesting this one. In fact, this alpha which is given by square root of omega mu naught sigma and writing omega as 2 pi f and substituting omega as 2 pi f and cancelling off this 2 will give you square root of pi f mu sigma or pi f mu naught sigma. Okay. And the expression that you have e power minus alpha z as the z propagating wave or the attenuation along z can be rewritten as e power minus z by delta, where delta is equal to 1 by alpha, which is equal to 1 by square root of pi f mu sigma or mu naught times sigma for a non-magnetic medium. Okay. And this delta is a very important parameter called as skin depth. Okay. This is called as skin depth, meaning that if we launch an electromagnetic wave into a completely lossy or conductive medium, okay, with an initial amplitude of A, then the amplitude decays exponentially as A e power minus z by delta. This is the z axis. So, this is the medium, let us say, which is medium 1. I have sent in the wave into the medium 2. We will have to say more about what happens when medium 1 and medium 2 interact, but for now we will simply assume that the wave that has been launched into the second medium, which is basically lossy and conductive, actually starts off with an amplitude of A at z equal to 0, but as you have seen here, the amplitude decays exponentially, and over say z equal to some 4 delta or so, the amplitude would have actually decayed almost to 0. Okay. The amplitude would be just about 1% of what it started out with. So, that is why this delta measures the depth over which the wave can actually, the typical width over which, that is important distance or the depth over which the wave can go into the lossy medium, can penetrate the lossy medium, is about 4 delta. Okay. So, delta is called as the skin depth, and it actually is important not only to know what is the depth, but actually is important in a practical scenario when you are designing shields. Okay. Suppose I have a source of electromagnetic waves and I want to prevent. So, I have some device, let us say. So, let us say this device is motherboard and these EM waves are being generated externally for whatever reasons, maybe lightning, whatever other reasons, or it could be that EM waves are generated by the motherboard and this device is, let us say, television or some other kind of a device that I am looking at, and I want to shield the electromagnetic waves between these two, right. The EM waves which are going to impinge on the device, if the device is not shielded, would actually simply go and fall onto or incident onto the device. However, if I build a metal, I build a metal chassis or I kind of build a metal ground around this one of thickness which is approximately 4 delta. Okay. The thickness of this metal would be approximately 4 delta, and please remember this delta is now dependent on sigma as well as the frequency. Okay. So, if the EM waves are coming in at 50 hertz, then frequency omega is very small, delta is actually going to be very small as well. Okay. However, delta is inversely proportional to this, right. So, delta we wrote it as 1 by square root of pi f mu sigma, and at low frequencies this skin depth will be larger, meaning that the waves can penetrate more into the metal or the lossy material, whereas when frequency increases the skin depth reduces. So, if you know that the worst case electromagnetic waves that would be incident on your device would be at 50 hertz, then if you build a metal house or you house this device inside a metal, okay, with a depth of say 4 delta as determined by the material conductivity, then that metal or that house is actually sufficient, or the thickness of the device is sufficient to withstand even when your f is say 2.4 gigahertz, which would come from your cell phone. Okay. So, this idea of what should be the thickness, which is determined by the material permittivity, the material conductivity and the frequency of operation, the worst case operation and best case operation, is not so straightforward as I have written, but this still gives you a basic idea of what to expect when you want to shield certain devices from electromagnetic interference. Okay. And the concept of skin depth of a material is very important in this case in order to determine the requisite thickness of the material. So, with this we stop our discussion on uniform plane waves in lossy materials. we will have to say more about the interfaces of these waves. So, as we have seen here that we start off with a wave in one medium and then we somehow said that the medium 2 will carry the wave, but exactly what happened at the interface and whether this I can just take the electromagnetic wave from one medium and then convert or push it into the electromagnetic wave into the second medium without any changes at the boundary is something that we have to explore, and we are going to do that in the next module. Thank you very much.